we start class, I'll let you circulate the one. Okay.
Yep.
All right, thank you. Yeah.
Would there be a review?
The homeworks are really the reviews for the test.
Okay.
What I probably will do is I'll probably put on some practice problems. So I may put on some practice problems, okay? But really, the homeworks, are pretty much the review for the exam. So speaking of which, why don't we get started? First, I want to go through a few announcements. Okay, so on our Canvas page, you can see that there's 2 assignments. So the first one is the homework set that I released yesterday. This is on the end of chapter 3. It'll be due Monday at midnight. We won't have covered all the material by the time it opens. So if you see stuff on z-scores and stuff like that, if you see material that we haven't covered, just don't do those problems yet, okay? The exam's going to be posted next Monday. It'll be due the following Monday. And so I posted an announcement, but let me just go through this kind of briefly so that you're aware of, what to be expecting. So, like I said, those are the start and the close dates for the exam. How long do you have to take the exam? Okay, you'll have 2 hours, which should be more than enough. If you have special accommodations, let me know, okay? And I can adjust the exam time accordingly. What materials can you use on the exam? Basically, you can use any materials. You can use your notes, you can use the book. You can use the internet if you want, just to research topics. But what you can't do is you can't use any individuals for help. So you can't use the internet to solicit help. Can't get help from any people, okay? And that includes a Sarai, okay? So you can't use people, but you can use any other reference you want. The format of the exam is going to be like the format of the homework. So 90% of it will be like the homework problems. 10% of it will be questions from the activities and stuff that we've talked about in class that may not be in the homework, okay? Retries, you can take the exam a total of 2 times. I'm a big believer in people redoing exams to learn material. But the one thing you want to be careful about is the following. If you suppose you start to take the exam and you're like screwing up in the beginning, you're like, wow, I was not ready. Take the whole exam. Go through the whole exam. Because there may be stuff that you'll mess up at the end of the exam also that you want to know about. So take it like you would a regular exam. Note what you don't know, what you have trouble with, okay? Go back, read that material, look at the homework problems that are relevant, then go back and retake the exam, because you only have 2 tries, period, okay? So use them wisely. Let's see, on the questions where you have to enter a numerical value, you'll have 2 attempts. for each of those responses, because you can type in things wrong and round issues, stuff like that. But multiple choice, you only have one chance, okay? And let's see, the exam will basically be 20 questions. But remember, each question can have multiple parts, okay? Yeah.
With that being said, if you were off at the 10th value just a little bit, would that be something you would look at and get partial credit for, or is it just wrong?
Well, if it says round and you round incorrectly, then that's really on you. And so you get an additional try, but you really want to be careful. This really is an exam. And that brings me to my last point, which is this. It's really tempting to think, because everything seems so casual and relaxed. I do this for a reason. I want you to be able to take the exam at your own leisure and an environment that's comfortable for you, that's convenient for you. But it is an exam. So when you take it like an exam. Put aside a 2-hour block of time where you'll be uninterrupted, where your roommate's not going to come in and bug you for a ride to the grocery store or something like that, because I'm not going to be sympathetic to that. Okay? So please make sure that you really take it like an exam. Take it seriously. If you have to go to the library, go to the library, okay? But take it like an exam. Take it serious, okay? All right, that's pretty much all I have to say about the exam. Any questions that you have? All right. So we'll see how it goes, all right? So what I want to do today is relative standing. So this is kind of the bridge. This is the bridge from descriptive statistics to inferential statistics. This is what lets us go from that small sample to that huge population. And so last time we started kind of posing some problems. This is a really great problem that kind of motivates a lot of what we're doing. This particular incident happened back in the 2008 Olympics and the women's decathlon. So it turned out that there were 2 contestants. One had a really great shot put. One had a really great 200-meter run. And they were pretty much the same in all the other categories. They pretty much were about the same. And the question is, how do you decide which one should get the gold medal? Now, the Olympic Committee has their own jacked up European way of doing things. Okay, I've never figured out how they do it, but there actually is a rational way of making this decision. Okay, and so we actually talked about this last time when we were talking about this thing of apples and oranges, right? So we gave this example of you have to lay off a person in some division you manage. One person's underperforming in IT, one person performing in accounting. You can't compare them directly. What can you do? Well, what you can do is you can compare them relative to their peers. So I might find out that Bob is in the lowest 10% of the IT people by some metric that I'm going to use to judge that department. And maybe Barb is in the lowest 25% of the accounting people. Now I can make a decision, an informed decision, right? Bob's performing worse overall. Questions? Just figuring out the role. I know that's always like a mystery, like how to get the role to everybody, right? That's like, I think that, I don't know. Anyhow, this other problem we had two job offers, right? Again, we can't compare these salaries because they're different locations, different standard of living. So again, one solution is to kind of look at where the salary stands relative to the people in New York City. And so you may find out that you make more with this annual salary than 87% of the people in New York City. With this salary in Daytona Beach, you make more than 98% of the people. And so, again, you decide Daytona Beach is better because your standing relative to the people in your community is higher. And so this is the notion of relative standing. It's going to look at where that value stands relative to the population, okay? So this is what we're going to look at today. Now the question is, how do we compute these numbers? Okay, so that's what we want to get at. And it turns out that the easiest sort of relative standing, kind of the natural way of doing this, is to look at the percentile, right? In other words, if I'm looking at some data value, and I compute its percentile, which is the percentage of values that are less than that, that gives me a measure of relative standing, right? It's kind of a natural way of looking at this. And we actually looked at some percentiles before. What was Q1? What percentile was Q1? 25th percentile, right? Q1, 1/4, right? Median was the 50th percentile, and Q3 was the 75th percentile. Now, sometimes when we have percentiles that are above the median, we talk about the upper percentile. So instead of saying something like Michael Jordan in the 90th percentile for height, right, we might say he's in the upper second percentile, okay? Now, when we're just talking about percentile, by default, we're always talking about this. And sometimes when people want to be really careful, they'll make a distinction. We'll talk about lower percentiles and upper percentiles. But when we just say percentile, we're always talking about what you might call the lower percentile, all right? And what we want to do is we want to start kind of thinking about percentiles in a graphical way, which is new. We're thinking about probabilities in terms of a graph. And so to kind of illustrate this, let me show you the data from activity 1. So remember in activity 1, we had all the building sizes, right? And if I made a histogram, it looks a little jacked up, but I'm doing this on purpose. I'm making a histogram that has a bin width of 1, because I want to look at the probability of each single building size, okay? You notice that I would get a relative frequency histogram that looked like this. So the smallest building size was 2. So this is saying that 2% of the data values had a size of 2, 8% of the data values had a size of 3. And that relative frequency histogram now comes in handy. We said before, we don't plot frequency histograms, we plot relative frequency. Because now if I want to look at the percentile of 3, notice I can get that right from this graph. I automatically can say 3 is the 10th percentile. Because if I add up all the percentages, right, of all the data values less than 3, I'm going to get 10%. So that's where that statement comes from, right? Now, there's different ways of looking at percentiles. And the one way of looking at it is you could say 10% of the data values were 3 or less. But if you think about activity 1, we had a different way of looking at it also. You could think of it as the probability. If you randomly chose a building like the computer did, right, it was going to have an area less than or equal to 3 to 10%. So we can kind of look at both ways, all right? So, let me switch to, okay. So notice that there's kind of another way of thinking about this. We can think about this really as the area under this curve, okay? 10% of the area under this histogram is right here. So we can start to say that the percentile of value is the area under the plot of its distribution. And so we're going to kind of sketch this out a little bit. So what I'm going to do is this is the relative frequency histogram where I've made the bin that's at a size of 2. Okay, so this is the interval from 2 to 4, not including 4, from 4 to 6, not including 6, and so on. And there's the relative frequencies above it. So now I'm gonna be able to interpret this as the probability in the left-hand tail. I'm gonna interpret the percentile of the data value as the probability in its left-hand tail. Now, what is the left-hand tail of a data value? When we've been talking about tails in the past, we've been thinking of something like skew, right? But now I'm gonna pick a data value, like suppose I pick 4 here, okay? And I'm gonna call this portion of the distribution on this side the tail of 4. Okay, doesn't necessarily mean it looks like a tail. It's just the portion on this side. Okay. So if I want to ask, what is the percentile of 6? Okay. So this is 2, this is 4, this is 6. So I'm going to look in the left-hand tail of 6. In other words, the portion of the distribution on the left-hand side. Okay. So this is the left-hand tail of 6. And I'm going to add up these probabilities. So that's going to be the percentile. So this is going to tell me that the probability in that should be left-hand. Sorry, I have to change that. The probability in the left-hand tail of 6 is the sum of these probabilities. This is the tail, and this is the probability in the tail. And so this tells me that 6 is in the 33rd percentile. 33% of the data value. We kind of have a graphical way of looking at this now. And we're going to see this is a natural way for us to start talking about probabilities. Probabilities are going to be percentiles. Percentiles are going to be areas and tails. And so that's such an important point. Let's go ahead and write that down. So we're going to say that when we talk about probabilities, the probabilities we're going to be interested in are percentiles. And percentiles are going to be the probability in the tail of a value. This is a very different way of looking at probability. We don't think of probability this way, okay? So what if we want to talk about the upper percentile? Well, the upper percentile is going to be the probability in the right-hand tail, the upper tail, right? So if I now ask what data value is in the 5th percentile, well, notice that these two add up to roughly 6%, right? So I would figure out that 15 was the 6th percentile, so it's going to be close to the 5th percentile. That's going to be the 5th percentile. That's the smallest data value that has 5% of the data values greater than it. Okay. Now, this is cumbersome, and it's a pain in the butt, and you really have to do it carefully, because you have to look and see if these endpoints are included, okay? So you might look at this and say, that's not really very satisfying, because I'm on the 5th percentile, and I really got the 6th percentile. And so this becomes a little tricky. So we're going to use stat crunch. Okay? So here's how stat crunch is going to work. We're going to go to summary stats, and we're just going to compute it directly in summary stats. We're going to see it's really simple. So let's go ahead and open up that data set. It's called, so this is in modules, right? If you go to modules, do you already have this downloaded? Did we already download this data set previously? We did? Okay, good. Then you should have that stored in my data then. We don't have to do any work. It's already there. So one of the things that kind of makes life really easy is whenever we use a data set in class, save it in StatCrunch. Then you'll have it in my data, and then you don't have to download it anymore. Makes life much easier. Okay. So I'm just going to download this from my data. Okay. And there we are. So let's go to summary stats like we did when we computed the mean and all that stuff, right? And so I'm going to go to stat, summary stat column, just like before. Click on building size because that's the variable I'm interested in, right? Click off of all of this stuff because it chooses by default like a boatload of stuff, okay? I don't really want that. And all I'm going to do is just enter the percentile here. So let's enter 10, the 10th percentile. So we're going to enter the percentile in percentage form, not in decimal form, and click compute. And what you should see is that we get 3, just like we found out when we looked at the graph, right? So I'll go back and just do this command really quick. And you should get 3. And that's what we found. We had to go through like a really torturous way of doing it, right? But that's what we ended up getting. Good. What would be the upper 5th percentile? How would I find that? I should type in 5, right, for the upper 5th percentile. Nope, you're shaking your head no. What should I type in? 95. And the upper 5th percentile is really low. It's really the upper 5th percentile, right? So let's go ahead and check out what the 95th percentile is. That's what I was trying to get before, right? The upper 5th percentile. And we see that it's 16. So notice something about histograms. We said it was 15 before. There's kind of this thing about histograms you have to be careful of, which is that, are you guys getting it okay? What happened? Okay. And you can always download it from modules too. You can just download it and start over. Yeah. Okay, so here's the thing about histograms you want to be a little careful of. This is a slight aside, but it's useful to think about. There was a homework question where it gave you a histogram, and the end of the histogram had some interval, like 0, right? So the histogram looked like this. Okay. Now, whatever, it was a histogram, right? And maybe the bottom bin started at 0 and it went up to 10. And it asked you what was the minimum value. It says, it asked you, like, was it 0? The answer is usually not. Okay? The histogram doesn't tell you anything about the values in here. It just tells you the interval and how many are in that interval. So we don't know that the minimum is 0. We have to go into the data set and actually use summary stats for the minimum to find out the minimum. And that's the problem with trying to compute percentiles from histograms. If we do it visually, we can't see very well. We don't actually know where the values are. So it turned out that when we actually did it carefully, it ended up being 16, not 15. So that's something about histograms you have to be aware of, okay? All right, any questions about computing percentiles? It's a piece of cake. It's a really easy command. And if you want to compute more than one percentile, you know, you can just put commas between them. So if I want to compute the 10th percentile, the 30th percentile, the 76th percentile, I just put commas and then it gives me all those. Piece of cake. Okay? Okay. Now we're going to learn two theorems today. These theorems are really kind of cool because they let us look at standard deviation in a totally different way. So up to this point, we've been thinking about standard deviation as the width of the distribution, right? Now we're going to see there's a lot more to it than that. Okay, so right now, you know, we said, okay, the standard deviation is the average distance of the data values from the mean. We said, okay, it's really good when we want to try to look at the reliability of a product. It's good for looking at the risk of an investment, where I talked all about that. Now we're going to look at standard deviation in a totally different way. A way that probably no one in this room would ever think it could be used. We're gonna use the standard deviation to calculate percentiles. We're gonna find out that the percentile of the data value is very often dependent upon how many standard deviations it is from the mean. This statement's really important. It won't make a lot of sense now, but we're gonna illustrate how to do this. And so the standard deviation, this is really a key point. The standard deviation is like a unit of measurement. One of the reasons why I use this textbook actually is one of the authors, Dick DeVoe, really emphasizes this, that it's just like a ruler. And we're going to see how this works. But this is a very different way of looking at standard deviation. This is not what we've been talking about so far. So let's see how this works. The first result we're going to look at is called Cheshevs Theorem. And he came up with a beautiful theorem. And what he said was, if you have any random variable, and you look at its distribution, we can say that the probability that any data value is k standard deviations from the mean, that probability is 1 minus 1 over k squared. So here's the mean, okay? And basically this data value is just 2 standard deviations from the mean. So the probability that you're within 2 standard deviations from the mean is 75%. Let me just illustrate this, okay? What this is saying. So this is called Cheshevs Theorem. The key thing about Cheshevs Theorem is that it works for any distribution. This is the strength of Cheshevs Theorem. It can have really strong skew. It can be unimodal. It can have outliers. Any distribution at all. So here's kind of the idea. So we're gonna start. We're gonna think of the mean as our origin. So we're gonna think of x bar as the origin. So here's x bar. And I'm going to step out in units of standard deviation. So this is going to be 1 standard deviation above the mean, 2 standard deviations above the mean, and 3 standard deviations above the mean. Okay? 1 standard deviation below, 2 standard deviations below, and 3 standard deviations below. And here's my distribution. It can look like anything. And so here's what Cheshevs Theorem says. It says that if I want to look at the probability that a randomly chosen value is within 2 standard deviations of the mean. So these are all the data values that are 2 standard deviations from the mean, right? This is 2 standard deviations below, 2 standard deviations above. It says the probability of finding a value in this interval is 1 minus 1 over 2 squared. This is the number of standard deviations from the mean, which ends up being 3/4 or 75%. This number here is the number of standard deviations from the mean. Okay? So this is kind of a nice thing to know. What about 3 standard deviations from the mean? Well, the theorem now just changes, because now we just say the probability here is 1 minus 1 over the number of standard deviations we are away, which is 8/9, which is roughly about 88.88%. So this is true for any distribution. What about 1 standard deviation from the mean? What's the probability that data values are 1 standard deviation from the mean? Let's just try the formula. So the formula says the probability that I'm k standard deviations from the mean is equal to 1 minus 1 over k squared. So when k is 1, what do I get? Not very useful, okay? So this ends up being 0. When k is 1, the probability is 0. So this is one of the limitations of Cheshevs Theorem. The thing that you're looking for has to be more than 1 standard deviation from the mean. Otherwise, it doesn't make sense. If it's less than 1 standard deviation from the mean, you get negative values for probability, which of course can't happen, right? So this is one of the limitations. Okay, you have to be looking at least 1 standard deviation from the mean. Any questions about Cheshevs Theorem? Yeah.
I was going to say, is it like you're just picking a random piece of data that this gives the probability that it's in that region?
That's right.
Then you run any piece.
Exactly. So you think of this as really like the plot of the data, right? So I just reach in randomly in the population that has this distribution, and what's the probability one of those guys is going to be 2 standard deviations from the mean? It's a beautiful theorem. It's really an amazing thing. Holds for any distribution. So let's go back and actually try this with the SOB data. Okay. So remember that on that SOB data, we looked at the prices for SOBs, right? We saw that X bar was equal to 29,500. This was the average price of a 2005 SOB, and the standard deviation was $3,500, right? And if it's okay, can I just write this in units of thousands of dollars? So I'm going to write this as 29.5, okay, in units of thousands of dollars, right? And this is 3.5K. I'm going to use Cheshevs Theorem now. So let's kind of sketch this out. So I'm going to write the mean right here. X bar is 29.5. Now I'm going to start stepping out in units of standard deviation. So I'm going to use a standard deviation literally like a unit of measurement. So what's one value above, what's 1 standard deviation above the mean? What should that value be? This is my mean and this is my standard deviation. What's 1 standard deviation above the mean? Okay, so how did you get that? You did what it said to do, right? You added the value for the mean plus the value for the standard deviation, right? So that's going to give us 33. Okay. So I just keep on adding 1 standard deviation, right? 2 standard deviations above, it's just 36.5, right? and 3 standard deviations above is just gonna be 40. What about 1 standard deviation below? What will that value be? We'll call on somebody new. What do you think? 1 standard deviation below, what will this value be? This minus this, right? So that'll give you what? 26, piece of cake, right? Then subtract 2 standard deviations off, I'm gonna get 22.5, and finally 3 standard deviations. I'm gonna be at 19. So this is literally like a unit of measurement. This is not an exaggeration or not, hyperbole. And it was kind of mound-shaped, right? It looked like this, kind of like that. Okay. And so we want to ask some questions now. Let's see, what is the probability that a randomly chosen SOB has a price between $22,500 and $36,500? What will that probability be? So 25%. How did you get that?
That's what it said on the previous slide.
What's in the previous slide? So here's the thing. He didn't actually look at the data values, right? What did you look at? You looked at how many standard deviations, right? So we said, okay, 22.5 is 2 standard deviations below. 36.5 is 2 standard deviations above. Cheshevs tells us that it's going to be 75%. And by the way, if I want to be really careful about this, Cheshevs says it's at least 75%. It could be more, okay? So I didn't put that in the theorem, but that's something to know. All right, good. Okay. Let's take a break. We'll come back. Did you have a question? I'm sorry.
No.
Okay, good. I don't want to, yeah. Okay, when we come back, we're going to find out that there are ways of kind of getting around these bad things. The fact that you can't compute something that's less than 1 standard deviation. This is actually very, very approximate, okay? We're going to find a much better way of doing that after the break. Okay. You know what? I can't do it on my computer because everything is hooked up. But you have like 3 minutes after class, right? Yeah. Okay. We'll get enough done. Okay. Thanks. Everybody get the roll. Well, I don't want to miss you. That's really small. Maybe that's what it's not, is it? Okay. So we're gonna look at it another method. So Cheshevs works for any distribution, but it does a kind of poor job. It gives really bad estimates. Okay, if you didn't have anything else, or you have a really weird distribution, it would work in a pinch. But now we're going to look at another one called the Empirical Rule. And now we're going to have to be a little more restrictive. So now we're going to have to only work with data that's unimodal and kind of mound shaped. Okay, it doesn't have to be perfectly symmetric. So mound shape is kind of vague, but as long as it doesn't have a long tail, it's okay. And basically, it's used to compute percentiles. And this is where this is really interesting. So now it turns out that we can actually compute the percentile of a data value. Notice that when we have the Cheshevs rule, we can't compute percentiles. Cheshevs rule doesn't tell you anything about what's happening in the tail. It only tells you about what's happening of certain standard deviations from the mean, what's going on in the center. But now we're going to actually be able to compute percentiles, knowing only the distance from the mean into the standard deviation. So now standard deviation really is like a point. Now, it's probably pretty obvious, but I'll just state the obvious, which is that you kind of realize now that the more standard deviations you are from the mean, right, the less likely you are to get that data value. Okay, so let's go ahead and see what the empirical rule says. So it says if you have a distribution that's unimodal, kind of mound shaped, okay, it says about 68% of the data values are within one standard deviation of the mean. About 95%. Notice that under Cheshevs, it said at least 75%. Now the empirical rule says if it's symmetric, you can make a much stronger statement. 95% of the data values are two standard deviations of the mean. And three standard deviations from the mean is almost all the distribution. Okay, about 99.7%. Some people say 100%. Don't say that, okay? The outliers are important. You're talking about intelligence, for example. That 0.3% of the population that's out here is sometimes really important. So we don't throw out outliers, okay, for extreme value. So this is a statement for the empirical rule. Sometimes people call it the 68, 95, 99.7% rule. All right. So again, let's kind of see how to actually use this, okay? Let's go back to the SOB example. Okay. So we know our means $29,500, $3,500. And we're going to use the empirical rule to answer these questions. Now, a piece of advice. whenever you're doing these sorts of calculations, it's always going to draw a picture. I've done this 20-some years, and I usually draw a picture. It's really easy to make stupid mistakes, okay? So let's try to draw pictures and answer these questions. So let's see. What is the probability that a randomly chosen SOB is going to have a value less than 29.5 thousand? What is that probability? What do you think, Jonathan? I know you just joined the class, so Jonathan's new to the class. What do you think? Just looking at the distribution, this is the mean, right? I have a symmetric distribution.
Yeah.
So the mean's equal to the median, right?
Yeah.
So what do you think that probability would be?
Probably the one we just wrote down there. Well, symmetric.
So notice that I didn't tell you one thing, right? Which is, what is the whole area under this curve? So you're going to say symmetric, cut it down the middle, it's half of whatever this is. What do you think the area under the whole curve is? You could say it's 1, right? If I want to think in terms of probability, or I could say 100% if I want to think in terms of percentages. So we have to kind of get a few things straight, right? So the area under the whole curve is equal to 1 or 100%. And so, exactly, it would be 1/2 or 50%, right? So we could say it's 1/2, or if we want to talk in terms of percentages, we could say 50%. Okay. 1/2 is more mathematically precise. 50% is how everyone talks, right? You never see the weatherman saying the probability it's going to rain is 1/2. They don't generally talk that way, okay? All right, good. And that we really didn't need anything except symmetry. There's not even any empirical rule. We're using the fact that for symmetric distribution, the mean is equal to the median, and the median is the 50th percentile. Good. What is the probability that I choose a randomly chosen value and the price is more than 33,000? How do I get that? I'll pick on you. So what do you think the answer is? You can kind of work it out. You don't have to know. What's that? Okay, so what are we thinking about with this data value? We don't really care that it's 33,000. This rule, what are we looking at? We're looking at what? How many standard deviations, right? So how many standard deviations from the mean is 33,000 or 33? It's one standard deviation from the mean. And what does the empirical rule tell us when we're one standard deviation from the mean? It tells us the probability that a randomly chosen value is one standard deviation from the mean. Tells us that it's 68%, right? Okay, so this area in here is 68%. Okay, but what area do I actually want here? Do I want this area? Okay, so you're saying that I'm interested in this area right here, right? Okay, so this area corresponds to the probability that x is greater than 33, right? Now, so kind of take us through the rest of this thing. Go ahead. Well, do you want to finish it off? I appreciate the contribution. Okay, so if this is 68%, what else do I know? So why we divide it by 2?
Because you're looking for the upper percentile.
And I know that it's symmetric, right? So the idea is that there has to be 32% in both of these tails in symmetry. These are each one standard deviation. Each of these has to be 16%, right? So that's where I'm going with that. So notice I made use of the empirical rule to get the combined probabilities in the tail, and then I use symmetry to get the probability in each tail. Okay? All right, good. Okay, so let's see. What is the probability that it's more than 19,000? I'll erase all this. Okay, and let's see. We'll stand this up, so I'll pick on you. So what is the probability of 19,000? So let's first of all figure out the area, right? What is the area? And then you're at a disadvantage, you're way over there.
Area.
What? So I start at 19 and I want all this area to the right, right? So this is the probability that it's greater than 19, it's all this area, okay? So how am I gonna find that area? You wanna give it a shot? Okay, so I know that this data value is 3 standard deviations away, so between 3 standard deviations is 99.7%. Does that get me everything I want though? Not quite. What am I missing? This little bit here, right? So it gets me the majority, but then I'm missing this little bit right here, right? So how do I find that?
Pretty much add it up, divide it.
It's the same thing, right? So there's 99.7 between 3 standard deviations, right? So there's 0.3% in both tails divided by 2. There's 0.15% in each tail. Okay? So I want everything except this little tail right here. So I'm going to subtract this from 100%, right? So the probability that x is greater than 19 is going to be 99.7%. This middle part here minus this tail right here. I'm sorry, plus. Sorry. Okay. So it's 100% minus just that little tail. Okay? Questions?
I'm sorry, how did you guys get that?
Okay.
Is that because it's like the outlier, like the 23%?
So there's actually 2 ways I can do it, right? First, I can take the probability that it's within 3 standard deviations. That's going to be my 99.7, right? And then I can add to it this tail, just like I did before. But that tail is really small. It's just 0.3 divided by 2, right? So each of these tails has 0.15. Or you can take 100% and subtract 0.15 from it. More than one way to count a skin, right? Right, good. Other questions? It's just like putting together a puzzle, right? Everything has to add up to 100%. And basically you're using what you know about the middle portion of the puzzle and then symmetry to get the rest. All right, let's try one last one. What is the probability that the values between 22.5 and 40? So now I want the probability that I'm between 22.5 and 40. Who wants to take a shot at that?
I'll give it a shot.
All right.
So, I guess help me get through this. So, do we need to, what is that, 77.5?
You mean 99.7, or here, I'll just erase all this. That's okay.
No, you said from 22.5, so that leaves.
To 40. So between this value and that value. Notice I can't use the empirical rule just flat out because they're not the same number of standard deviations, right? So I'm going to have to be a little more creative.
I'm not really sure what that was.
Okay, so what do we know? Let's kind of start off with what we know. Okay. What do we know?
We know it's at 22.5.
What's that?
We know to start at 22.5.
Which is how many standard deviations away?
From 40?
From the mean. We're always looking from the mean. This is kind of like our origin, our starting point, right?
Okay, so it's 2.
2 standard deviations here. Okay. What about 40? How many standard deviations is it away?
3.
Okay, it's 3. Okay. And what does the empirical rule tell us? So here, let's go ahead and shade this in. This is what we want. We want this area right here, right? This is the area that we want. Okay. How can I do this? Go ahead.
calculate 2 standard deviations away, divide that number in half, and then calculate 3 standard deviations, cut that in half, and add the 2.
Exactly. So here's the idea. The idea is that 2 standard deviations is 68, right? Symmetry tells me this has to be 34%, right? So this area here has to be 34%. This rule tells me it's going to be 99.7, so I'm just going to divide that by half, right? And that sum is going to be my answer, okay? So you go ahead and do that. So that's going to be what? 49.85, okay, plus 34, and so we just go ahead and add those. So we're going to have 34 and what, 49.85. That's going to be 83.5. Yeah.
Where'd you get the 34 from?
So I know that there's 68% between 2 standard deviations, and this is half of that, right? So the 34 is equal to the 68 divided by 2.
Wait,
I
I thought that
thought
was 1.
68 was between 1 standard deviation and 95.
You caught me. You caught me. Okay, you're absolutely right. I knew the answer looked too small. This is what should the correct one be?
95.
95, thank you. 95 divided by 2, so this is 47.5. Thank you. Okay, so everyone sees that? What did I use? I used what? 1 standard deviation away, so I was a bad boy. All right, thanks. Okay, now when we do this, right? So let's see, this is what? 97.35. That's going to be the correct answer. Another way you could have done it is you could have said, okay, 3 standard deviations and 2 standard deviations are contained, 2 is contained within 3. You could have taken that difference between 99.7 and 95, right? And that would have been this little area between 2 and 3. And then you could have just figured that out, divided that by 2, and subtracted that off too. So basically, another way you could have done it is this. You could have taken 2 standard deviations, which is 95, then 3 standard deviations, which is 97.5. Taking this difference, that would have been what? 2.5, right? I'm sorry, 99.7. Wow. Watch me today, I'm sorry. So these tails would have had 4.7, and each tail would have had 4.7 divided by 2. And you were interested in this part right here. There's a lot of different ways of doing it, okay? All right. So questions? Everybody's good? Okay. All right, thanks for catching that. Sorry. All right. Okay. So the last thing I'm going to end on today, and we're not going to get very far, but I'm just going to end here. Questions? No? Okay. Just a second. Okay, so here's kind of the idea, is that when you think about it, really, we're not, like I said, we're not interested in the data value. We're just interested in how many standard deviations it is from the mean. So we're going to start computing this thing called the z-score. Notice that if I'm working with a sample, I'm going to use the sample mean and the sample standard deviation. But this is just telling me how many standard deviations I am from the sample mean. Notice that it's signed. The data value is below the mean, the z-score will be right. And the data value is above the mean, it'll be positive. And if I have a population, I'm just going to substitute the population mean and the population standard deviation. And so we're going to see that this is how we're actually going to start really thinking about data values now, is we're going to start doing this. We're going to basically just put down the number of standard deviations. So if it's 1 standard deviation above the mean, it'll be +1. This data value is +2. This data value is +3. This data value would have a z-score of -1, -2, and -3. And that's how we're going to start thinking about data values when we want to compute percentiles. So notice something. Notice that to have a z-score that has a magnitude bigger than 3 is very rare when you're working with the empirical rule. In a model-shaped data, it's it's very unlikely you're gonna get a Z-score cut at size bigger than 3 on either side, okay? And so we'll come back, we'll pick up here, we'll stop here now, okay? Any questions before we end? Everybody's good? Okay, all right, thanks a lot, I'll see you on Thursday. I'm sure I did.
I just wanted to make sure that my attendance was okay. And then I had one question about it.
Okay, sure. Just give me 1 second. I'm just gonna finish this up. Yeah. Oh, excellent. Okay, thanks.
Sorry about the I had a transmission failure, literally. My
No,
transmission failed.
that happens. That's okay. That's all right.
$10,000.